Okay. Let's proceed. Let's proceed. Another day, another couple of LeetCode problems. Let's see, what did I want to start with today? Should we take a look at some Clash of Code first? Let's do like one or two Clash of Code. It's kind of fun. It's pretty quick. Just a nice little thing we can do to start out. So let's join a Clash. Oh shit! How are we starting already? With only 3 people. Okay. Username must have 3 characters, no more than 20. Only consist of. Oh, okay. JavaScript. Console.log. Regex.match. Oh no, it's string.match regex. So readline dot match question mark valid invalid so we need this symbol, we need A to Z, A to Z, 0 to 9, 320. Is that right? What did I mess up? What did I mess up? Shit. Let's copy and paste. Let's copy that. What was the original code? It's just read line and an answer. Okay, read line dot match. Do I need? Okay, so does this section need to be wrapped in? Fudge, dude. Have at least 3 letters, have no more than 20 letters, only consist of letters and digits. Yo, what is wrong with that regex? That looks right to me. Oh, wait. Why is it's the 320 is not right? Wait. JavaScript, fuck, I bet I already lost this one. JavaScript regex, I don't even know, dude. Yeah, that's what I'm doing, dude. That's exactly what I have. Python, what if I were to change this? Oh, is it because I have a space there? Oh God, was that it? Was that it? I had a space there. Submit. Bro, that's so frustrating. My regex was right. I just had a space. Okay, I'll share my code. He didn't share his code. Demonly7, you did not share your code, so I can't look at it. But okay, that was frustrating because I knew exactly how to do it. I coded it up quick, and I lost just because I had a stupid little shitty bug. But yeah, so that's how you do it. Okay, let's play again. Okay, we're in fastest mode again. Okay, a pet shop sells canned cat food via its online store. For delivery, all ordered cans are filled with boxes of 2 different sizes. Large boxes have a max capacity of L, small boxes contain S. When a customer buys a certain number of cans first, the delivery service fills up large boxes. Afterwards, all remaining cans. Thus, large boxes are delivered only completely filled. Small boxes are either full or partially filled. None of the delivery boxes are empty. You must output the number of large boxes and the number of small boxes for delivery of N cans. Okay, this seems like simple math. So N is the number of cans. N divided by the number of large boxes. No, sorry, the capacity. And then we need to floor that. Is that right? Followed by S divided by, so the whatever the number of cans left over is, so math.ceil n mod L divided by S. I just made up that math on the fly. No idea if it's right. There it is. We win. We win. Okay, so the solution is just some simple dividing, finding quotients and finding remainders. So the number of large boxes you use is just the number of delivery cans divided by the capacity of the large box, and you floor that because you're gonna get a fractional value because JavaScript. So now if you take n mod L, that's going to give you the remainder of the division, and the remainder will tell you how many cans you have left to put in the small boxes. So then you divide that number by the capacity of the small box, and then that number you have to ceil, because you could partially fill the small box, so you could get it like 80% full, but you still need to round up and say that there's one small box. How was this clash? Fun. Difficulty. Perfect. Statement. Statement clear enough. Test case relevancy. I didn't even look. I just kind of saw that I was getting greens, and I just clicked the submit button because I felt decent about this one. How long is it gonna take our friends here? Man, the longer it takes them, the more inflated my head gets. It's literally growing. No, I'm joking. These can be tricky for people who are just starting out. Let's play again. Oh, this one starts immediately. Okay. Okay, fastest mode again. For each line of 3 numbers, you have to find the number with the middle value. Oh. So if x is less than y and Is it guaranteed that there's a middle value? We'll just make this less than or equal to. And y is less than or equal to z. Console.log y. Oh, someone. Then if z is less than x, wait, no, this is easy. What am I doing? Fuck, someone's gonna get this now. We just sort them, obviously. So sort A. Oh, it's a dot sort. Okay. We get second place. I could have won, but I was like, oh, there's only 3 numbers. I should just compare, you know. But still, the fastest way to code it up would be to sort the 3 numbers and just grab the middle one. This person did it in Ruby. Let's see. Yeah, pretty straightforward. All right, I like fastest mode the best. Okay, we got some other people finishing up here. Not sure if anyone's gonna share their code. Let me look at my code again. Let's go back to compete, Clash of Code. Oh wow, my ranking is going up. Let's see, is there a way I can specifically ask for fastest mode? Because I don't care about shortest mode. Shortest mode seems so dumb. Like it makes you learn techniques for doing something that you'd never need to do in a real situation. Okay, maybe I'll do one more of this. Okay, join a clash. I like to start off the stream with a little bit of clash. And then after clash, I have something exciting to announce. No, I don't have a job yet, but I do want to announce something. Then there's gonna be LeetCode, and I think later on there'll be a segment where we look at strongly connected components, because I need to I understand what they are, and I understand like when they're useful for the most part, but I need to refresh my memory on an algorithm to generate them. So there's an algorithm called Kurosawa's algorithm for strongly connected components, and it takes a directed graph and it tells you what the strongly connected components are, So I need to refresh my memory on the implementation of that. And then I picked out a LeetCode problem that, according to the related topics, should require us to use strongly connected components. So yeah, so I'm going to refresh my memory on SCCs, and then I'm going to try to solve that problem. Also, if anyone at any point wants me to like diagram something out, I have this like pen tablet set up now. So, you know, I can draw shit here. I could make a little graph. I could make a little tree data structure. You know, like that. Oh shit, we're starting. Okay, here we go. Fastest. We want fastest. We don't want shortest. A reverse mode. You have to guess what to do by observing. Okay, it turns all of the X's into O's. Or all the O's into X's. Is that all it does? If r dot includes, does it work with lowercase o's too? Oh man, I can't even tell. Oh, someone's already done? Bro. If r dot includes, let's just try then console.log r.replace x with O. I don't know if this is right. Man, that's intimidating when someone gets it so fast. Let's just try this. We need to replace all, which means we need to, we can do that by using a regex with the global flag. Man, 3 people got it already, bro. I think what happened was my rank like jumped up, and so I actually got paired up with like players closer to my elo. What? Oh, else. Submit. Okay. That was not great. Well, we got it. So at the very least, we got it. Our approach was, if we find an uppercase X, we replace all the uppercase X's with uppercase O's. If we find a lowercase x, we replace all the lowercase x's with lowercase o's. It gets accepted, but let's see. This person solved it in 46 seconds. Oh, this guy, we competed against this guy earlier, Batu. Let's check and see what he did. What? G-sub OX? What does G-sub do? Does it just flip them? Apparently you didn't have to worry about uppercase O and X. I couldn't tell from looking at the input that that was the case. Let's see, Ruby G-sub. Java's the G-sub looks like it's just the same thing as JavaScript's replace function when you pass it a global regex. So I probably overthought it a little bit. Apparently you only needed to worry about O becoming X according to his code. So should I do one more? Let's do one more. I don't want to say play again till I win. I have no idea how long that could take, but I will at least do one more. Let's see. Hopefully Batu is not in the game because he's really good at this, obviously. Come on, get us in there, get us in there. Get us in there. Don't be shortest, don't be shortest. Don't be shortest. Fastest mode. We define transformation of digits as being from that, you're given n digits as input, please transform the digits in a similar way. For example, if you're given the digit 1, you should output the digit 8. Oh, wait. C++. String answer console.log answer equals. Oh shit, someone's done. Oh, someone's done and they did it in C++ too. Yeah, I think this is just adding a value to a character and then maybe modding it, which is why I started to do it this way. So Philip Plank. I hate how they put these comments in here. Okay. So for oh, it's inputting it as an int, bro? Don't do that. Input it as a string at least. Okay, so for char c in x. So we basically take it. We add 7. Okay, so what exactly is happening here? 0 becomes 9, 1 becomes 8. Okay, hold on. I'm really noobing out on this one. Let me try to do this in a different language real quick. And I think this will probably be the last coding game. Okay, so just read the line. So let me try to do it this way. So const a equals this. Const b equals this. X.readline, let ans equals empty string, console.log the answer, then for const c of x ans plus equals, and then it's going to be b, and then the index of a dot index of c. Okay, that looks right. All right, that was not quite the performance I wanted out of that one, but we did come to a solution. Philip Planck solves it in 46 seconds. Very impressive. Let's see. Oh, really? That's all you have to do. 9 minus the number. So did they actually fix that? I remember this used to be a problem, and it looks like it still is. Not being able to go back and see the problem description after the contest is over. Okay, let's see what other people did. 9 minus the number. Okay, this person did something a little different. And then my code. Hey, you know what? Working code is working code. Okay. So, I had a phone screen with Amazon today, and I don't want to jinx it, but I think I passed. Anyway, I'm trying to train myself not to get my hopes up, but I did have a phone screen where I had to answer a few behavioral questions, and I had to then I had to do a coding challenge. The behavioral part was tricky. I just did the best I could, honestly. Tried to pull from my experience. But then the technical part, the technical coding part of the interview, I think I breezed through. So what I wanted to do was go over the problem that was asked in the interview. And so I went to LeetCode and I tried to find the exact same problem on LeetCode. I don't think it exists, but the closest thing I could find was word search 2. And interestingly, if you look at companies that ask this question, Amazon asked this question 29 times in the last 6 months. However, they didn't ask me this. They asked me something similar to this. They didn't ask me this. So and I'll explain what the difference is as well. So given an n by n board of characters and a list of string words. Hold on, let me also share this in the Twitch chat. Given an n by n board of characters and a list of strings words, return all the words on the board. Each word must be constructed from letters of sequentially adjacent cells, where adjacent cells are horizontally or vertically neighboring, and the same letter cell may not be used more than once in a word. Okay, so this is very similar to what I had to do. I did get an m by n board, and I did get a list of string words, but in the problem that I had to solve in my technical phone screen today, it was like a normal word search where you're just looking for words that are in straight lines, either horizontal, vertical, or either of the two diagonals. So in my solution, in my solution, I built a trie, aka a prefix tree, out of the input words. And I'm gonna need to do that for this problem too. However, in this problem, I need to do backtracking to get the solution, whereas in the problem that I did in my phone screen earlier today, it was simpler than that. So what I needed to do was just iterate through the grid one cell at a time. Then for each set of coordinates in the grid, each cell, I then need to go in the 8 directions around it in a straight line. So like I go up one across one, and then as soon as I go up one across one, I'm then going up one across one every time until I find a full word. Or multiple full words. And so the prefix tree makes it easy because you basically create a data structure that lets you look up words that are starting with a certain prefix really easily. And the prefix tree is also going to be useful for this problem because you can go in any direction. So what we'll do is we'll use a prefix tree, but we'll also use backtracking. Okay, so I'm gonna solve this problem. I do need to take a quick bathroom break. It won't be very long. And then as soon as I'm back, we'll jump right into the code for this one. So, prefix trees. We need a prefix tree. So for example, let me explain what a prefix tree is. So what is a prefix tree? Let's say that you're given some words, right? Let's say that you're given apple. Whoa. Why is it so small? Am I zoomed out really far? Come on, why is that Excalibur? What are you doing to me, bro? Okay. There we go. So we're here. Okay. All right. Apple, app, bear, bee, and Okay, so these are the words for the prefix tree. So the way it works is you're basically gonna have a tree that keeps track of prefixes. So at the top, you're gonna have a node, and then the top node is just like you can think of it as a root that represents the start of the word. And then underneath the root, you're gonna have nodes for each letter, each first letter that there are. So we have two first letters, we have A and B. And then it continues. So now you have A. What's the next letter? The only one that it could possibly be is P. So you have a node for that. P, P, and then you're going to have an L, and you're going to have an E. Let's move these around a little bit. I haven't done much with the pen, so I'm getting used to it. Go again. So it's going to look like this, and then you're going to have arrows connecting these, which is why you think of this as a tree. So for B, let's add more nodes in. You would have a B, E, A, R. Now what's really interesting about the prefix tree though, that B, E, A, R. So this, what we have here kind of represents the word list that I provided, but it doesn't actually show you what's good about prefix trees, really. Okay. So in the prefix tree, we also need to be able to keep track of which nodes correspond to the ends of words. So, for example, a corresponds to the end of a word, and so every single node here that corresponds to the end of a word, we want to flag it. So we can just give it like, I don't know, put like a little diamond in there, right? So the A, this P, and this E, and this E, and this R. So the nodes that have these little diamonds in them correspond to the ends of words. And so effectively what we have now is we have a prefix tree representation of here we go. Hold technical difficulties. There we go. So this list of words becomes this, right? And so if we were to add more words, let's add more words just to demonstrate the power of the prefix tree. What if we had another word? Belt, right? So for belt, we already have the BE. So now we just need two new nodes. We need the L and we need the T. And so we can do it this way. And so essentially what we're representing is that belt and bear have a common prefix, which is this BE right here. Boom! There it is. So there's, oh wait, we're missing one thing. We add a little flag by the T to indicate that it is the end of the word. So what else can we observe about the prefix tree? If you look at the nodes that have stars and you count them, 1 star, 2 or diamonds rather, 1, 2, 3, 4, 5, 6. That is guaranteed to correspond to the number of words that your prefix tree represents, which is these right here. Also, I guess I should, yeah, make sure that this is in view. So you have this. Okay, so we have that. So that's our prefix tree. So now we're going to write code to actually build this. But I just wanted to explain what it is for anyone who maybe didn't know. Okay, so let's go back to the code. And the way that we're going to make the prefix tree is we're going to actually create a class for it. Class, and we'll call it try node. We're going to have a class for the nodes. Just like that, and public. So all we need is, so for every node we need to keep track of what the children are, right? So for the root node, for example, the children would be a map from a character to another try node. So you'd have an unordered map from char to try node star, and this would be the children. And then the other important thing to have is you want to keep track of which try nodes terminate. Terminate meaning that the node, it represents the end of a full word. Terminates equals false. Then you want to be able to create the try node. So try node build try, and all it takes is the vector of string words. That's all you need. Okay. Now, the first thing we need to do to build the try is we need to make the root node. So try node star. Okay, and we'll just have it. We'll have it return a pointer. Try node star root equals new try node, and then we'll return the root at the bottom. And then down here, what we'll do is we're gonna just grab that. So we'll have a try node star try equals build try from the words, just like that. Okay, so the way you build the try is you just go through all the words one at a time and insert them into it. So how do we do that? Well, we iterate through all the strings. So for a string word in the words, and then for every single word, we want to insert the word into the try one letter at a time. So for example, if we go back to our diagram, if we're let's say that we already had the word bee in the try, but now we're trying to insert the word bear. We'd start at the root, then we're starting at the first letter of the word we're inserting. So we would see that the bee's already there. We would go to it, get its children. We would see the e's already there. And then now we've already done the first two letters of bear, but there's no, at that point, there's no A as a child of the E. So you create it. So you basically only create the nodes that you're missing, the nodes that you still need. So let's do that. So for char C in word. Okay, and then the other thing that we do is we need to keep track of the current node in the try that we are. So we'd have like try node node, and it starts off at the root, like that. And then we need to see if the current node, so if the current node doesn't have the child, we need to create it. So if if the node's children at C doesn't exist, then we need to make that. So it would be node children C equals new try node. And then we go to it. So then node equals node children C. That takes care of that. Let's see. Okay, all right. So there's one last thing we need to do. After we finish inserting all the characters of the word into the try, once we finish the last character, the for loop terminates, but the value of node will be the value of node will be the last child that we inserted. So then we need to flag that node as being one that terminates. Boom! Okay, so let's see if we're syntactically correct as of right now. Okay, semicolon after the class. Okay, so we're syntactically correct. Alright, so what's next? So once we build the try, let's assume that the try is right for now. If it's wrong, we'll discover that it's wrong later. Okay, so let's just review the problem statement. Each word must be constructed sequentially. The same letter cell may not be used more than once in a word. Right. Okay, so So I think this part is pretty similar to what I had to write earlier today during my Amazon phone screen. We basically start at every cell. And we start at every cell, and we try to start building words from that position. So let's get int n equals board dot size, and int m equals board 0 dot size. Like that. You're guaranteed to have at least one cell on the board, so I don't need to check for like an index out of bounds here. Always good to just look at that real quick. So I is less than n plus I, and then for int j is 0, j is less than m plus j. All right, and then the character at this position is board ij. And so the idea is that we're in the try, right? We're gonna start looking in all. Can it go diagonally? Oh no, it's only horizontally or vertically neighboring. So we can only go 4 directions, but we're gonna start a backtracking algorithm that goes all 4 of those directions, and tries to find words. Okay, so what do we need to do? Well, we need our directions. I'm gonna write the directions thing a specific way that I usually write it. So your directions array is 1, 0, -1, 0, 1. And the idea here is that the consecutive, every pair of 2 consecutive elements of the array here represents a direction that you can go. So the next thing to do is go every direction. Oh no, we don't. We actually, the next thing to do is to backtrack, and then inside the backtrack call is where we'll go in all the directions. So let's create a function. Should I create it as a part of this class? It doesn't really matter, but I can. So I think it's gonna end up being bool backtrack, and it's gonna take as input, it needs the board. Sorry, yeah, it needs the board, so copy the board definition. It needs the like current try node, so try node star node that we're at. It needs the coordinates. It needs the coordinates. It's gonna need the dimensions, so we'll pass those in, and then also as we're backtracking, as we're doing the backtrack algorithm, we're producing our answer, so it needs a vector of strings. That's a lot of parameters, but that's all the stuff that it needs. So, oh, it's also gonna need, it's gonna need something else too. I think it's gonna need to keep track of like where it's visited on its current traversal, because you're not allowed to use the same cell more than once in a word. we're going to have our vector of string answer, and we're going to return that. Okay. So, since this function takes so many parameters, let's just put them all on lines of code by themselves. Yeah, and then as I mentioned, I think we might need a visited. Well, no, we can probably just update the board, right? Like, board IJ is a lowercase English letter. So I could like replace it by a pound sign or something when we visit it, and then unreplace it by a pound sign when we come back out, when we backtrack. So I'll try to do it that way. So let's pass everything in. So backtrack, board, try, everything. So everything starts off at the root, I, J, and M, answer. And I don't think we need that. I think this might be fine. So we're gonna start from, let me think about this, because when you're at a cell, there could be multiple words that you're gonna find like from that cell. So for example, let's say if we look at the example 1 here, you can see that it found oath. But if oat had also been something in the input, it would find both of them at the same time. Like it would find oat first, it would put it in the answer vector, and then it would go one farther and find the H there, and it would put oath in the answer vector. Oh no, but this is still gonna work though. Yeah, this is still gonna work. I think this is gonna work. Okay, so let's think about this. So we're iterating through every single cell in the board, and we're starting to backtrack from that cell, passing in the board, the root of the try, I, J, N, M, and the answer. Okay. Okay. I think this is one of those backtracks where it can just return void, but we'll find out in a sec. So what do we need to do in here? So we need to, there's 4 different directions we can go. So let's go those directions. So IDIR equals 0. IDIR is the index of the direction. IDIR is less than 4 plus IDIR. And then we're going to get our next I is going to be I plus dir sub IDIR. And then int nj is going to be j plus dir of IDIR plus 1. And so that's going to give us all 4 of the next tiles that we want to look at. So we need to make sure they're in bounds. So if ni is less than 0, or ni is greater than or equal to n, or nj is less than 0, or nj is greater than or equal to m. We continue, we can't go that way. And furthermore, oh no, that's it. So we know it's in bounds, so now we're gonna try to go there. Oh, and then we also need to, as we're going through this backtracking process, we're keeping track of like a current word. So we have a vector of char, which is our current word that we're building. Vector of char current word. That's fine. And we'll also pass that in here. Vector of char reference current word. So importantly, there are a few things that we need to check right here. So if we come into a backtrack call and the current node terminates, then whatever is in the current word, we need to squoosh it into a string and throw it in the answer. So if the node terminates, oh, also if not node, return. So if we get a call to backtrack and there's no try node, right? Then there's nothing to do. We can just return. However, if the node terminates, then string word equals empty string for char c of the current word, word plus equals c. And answer dot push back the word. Yeah. Okay. So after we check those things, now we go in all four directions and we backtrack. How do we backtrack, you might ask? Well, quite simply, we pass in the board. We have to get the children of this node, but only for the new character that we're going to. So it's going to be children subboard ni nj. And so this is where this base case up here comes in. If we're looking for a character that's not in the tree and in the prefix tree anymore. Oh, Gigantic Bucket, what's up? Do or do not. There is no try. Sorry. Good luck with the algos today. Thank you. No, that was funny. So yeah, you might have missed it, but I explained a few moments ago that I had a phone screen with Amazon earlier today, a technical phone interview. There were also some behavioral questions. And this LeetCode is fairly similar to the problem that I had to solve in the interview. Although this LeetCode is actually a little bit more difficult. In the interview, I only had to search in straight lines. So you go in like the 8 directions around a cell, and you're still iterating through the try, but you only go in a straight line. This problem, word search 2, adds the additional complication that you don't go in a straight line. You can literally go anywhere. Left, right, up, down from any position. So we try to get the child node. Then we pass in our new I, our new j, our n, our m, our answer, and our current word. Okay, so a few more things though. Current word plus equal, oh no, we have to do current word dot pushback board of ij. Okay, so this line of code, I think goes up here somewhere. I think it went good. I think the technical portion, the coding portion, went really well. I got a full implementation where I had a full implementation of building the try, and I had a full implementation of searching the puzzle using the try. And then the behavioral part, which was the first part of the interview, I think it went fine. Like it was definitely the part of the interview that I was less prepared for probably than I should have been. But you know, I just tried to answer the questions as best as I could and pull from my experience. And I think honestly, I don't want to jinx it because I don't want to get excited. I don't want to get my hopes up. But I think it's going to be a pass for the phone screen, and hopefully, you know, assuming it is, I've got plenty more time to prepare for the, you know, the behavioral section of the full set of interviews. Okay, so if there's no node, we return. If the node terminates. Okay, so I think this goes here. So we take the current char, we push it into the word. So let me just think about this in terms of being at position 0, 0. Current word is empty. Try is pointing at the root. So we come in here. That's not going to happen. And then we take the letter at 0, 0. We add it to the current word. And then hypothetically speaking, if oh, okay, no, it's not going to work because this node corresponds to like the previous node in the tree, not the current one, because it starts off being the root. How you doing today, Gigantic Bucket? Are you doing some problem setting? What's your favorite problem that you've ever written? If you have a link to somewhere that it's accessible online, I'd love to take a look. Okay, so if the node terminates, so the root node cannot terminate. Yeah, okay, so I think that this does belong down here. So I go in all 4 of the directions. Oh, no, okay, so I think this is it. I push the letter from here on, then I go in all 4 of the directions. Then after I go in all 4 of the directions, trying my darndest to find matches, then I pop it back off again. Current word dot pop back. Is that it? No comma there. Oh, interesting. Okay, so I'm getting some output, but it looks like a hot mess. Chilling with the doggo, nice. So the other thing that I coded this up. I actually do still need to validate that it's correct, this build try step. Should I debug this? because it's getting some weird stuff. Like it's producing an answer, but it's just producing like garbage that's absolutely not words that are in the allowed word list. Let's see. So if there's not a node, we return. If the node terminates, then we just build a word real quick out of the current word and we put it in the answer. Then we take the current letter. We take the current letter from the current cell, put it in the current word. And we go in all four of the directions. NI, blah, 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 boundary checks, board, node children. Oh, wait. Take a step back. This is not right. I have to go to the node in the tree for the current character. So this should be node children board I, board J, I think. Okay, that looks better. Except I'm producing the answers 4 times. Oath, eat, instead of just oath and eat. So let's see, is that because of my code, or do they actually exist that many times? Okay, yeah, I think... So I guess the answers is just supposed to be a set. Oh, wait a minute. So this is where one of the optimizations comes in. So what I could do is my vector of string answer could be a set or an unordered set string of answer, and so that makes sure that I only keep every word once. And then down here, before I return the vector, I have to turn the unordered map, or sorry, the unordered set or set into a vector. However, I could destroy the prefix tree as well as I go. Because after I find a word, I no longer want to find that same word again. So that could be an interesting optimization. Also, I do need one thing I'm not doing is marking cells as visited, because you're not supposed to revisit the same cell in the same word. So here's what I'm going to do. Char C equals board I J. Current word pushback C. And this right here will be children of C. Now after I grab it out, what I want to do is change board IJ to be something like, it could literally be anything. I'm gonna make it %. And then after we finish that backtracking, then we just change it back to what it was before. Okay. So I still think that was something that needed to happen. But that didn't solve this problem where it's finding O-A-T-H. So as far as eat, there's an eat here, there's an eat here, there's an eat here. So I see 3 eats. Hold on a minute. Bubbly Troubly on Caddis. It's been a long time, but I have actually used Caddis. You may have seen a champagne tower at a wedding or an exclusive Hollywood. Wait, so are you like a PhD, like computer science professor? Or are you not? And like you still do this like for fun? I'm curious what your background is. It's attributed to John there. That's not me. He was the head judge. Okay. You may have seen... Nah, I helped out for fun. Gotcha. Yeah, the only reason I ask is because when I was in college, my computer science professors liked to write these. And yeah, so I was just wondering if that was you as well. You may have seen a champagne tower at a wedding or an exclusive Hollywood... Right, almost all props behind these. Typical 3-level tower. The first lowest level contains 9 glasses. Second level contains 4 glasses touching in a square pattern. And then, okay, so that makes sense. Champagne is always poured directly into the top glass. In this example, once the top glass fills and starts to overflow, it immediately begins filling the 4 glasses below. Assume overflowing champagne travels instantaneously to any glasses below. Once the 4 glasses on the second level fill, they begin overflowing to the 9 on the bottom level. Interesting. Note that in this example, the 4 on the second level finished filling at the same time, but the 9 on the lowest level finished filling at different times. That means there will be some amount of spilled champagne before the tower has finished filling. Why is that? Why do they not all fill at the same time? Oh, okay, because each champagne glass is emptying in 4 directions at the same time, but the middle glass on the bottom level is receiving champagne from all 4 of the glasses on the second level. Got it. There will be some amount of spilled champagne. This is an acceptable price to pay for such a beautiful sight. The new fad is to make interesting patterns or imagery out of champagne glasses. These newfangled towers needn't appear structurally sound. They can be held in place with complex support systems designed so as not to interfere with the overflowing champagne. Each of these new towers will always have a single highest glass into which all the champagne is directly poured. If 2 glasses rims coincide vertically, i.e. have the same center and radius, then no accumulation occurs in the lower glass from the upper glass, though the overflow champagne from the upper glass may still be collected by other lower glasses. Additionally, a single point of champagne overflow causes no measurable accumulation. In other words, measurable accumulation only occurs when a non-point arc of champagne overflows to the interior of a glass. Whoa. I don't even know if I follow anymore. I understand that when they're exactly over top of each other, there's no accumulation in the bottom one. A single point of champagne overflow causes no measurable accumulation. In other words, measurable accumulation only occurs when a non-point arc of champagne overflows to the interior of a glass. Oh yeah, that's just talking about like the intersection of the curves from the top. Like if the circles viewed from the top are tangent. Like right next to each other, touching but not overlapping. Then there's no accumulation. Okay, your task is to determine whether a proposed champagne tower will fill to completion, and if so, how long it will take. Okay. Yeah, I feel like figuring out whether or not it will fill to completion is an easier problem to solve than how long it will take. Because whether or not it fills to completion, you just have to make sure that every single glass is going to accumulate from above, from somewhere. let me see what the input is. I don't think I'm gonna solve this, by the way. I'm just curious about it. The input begins with a single integer n representing the number of champagne glasses in the tower. The next n lines each describe a champagne glass. Each glass consists of 5 values, x, y, z, r, v, with x, y, z representing the center of the glass's rim. Okay. R representing the radius, and v representing its volume. All input values are integers, and the top glass is filled at a constant 100 milliliters per second. So this definitely seems like it's a math problem combined with like a graph problem, because you have to do math to figure out where the accumulation is going to happen, like where the overflows are going to connect with champagne glasses below. But then once you figure out those relationships between the champagne glasses that are higher up and the champagne glasses that are below, then you can do graph theory. You may assume that any two glasses that have the same z coordinate will not intersect, though they may touch each other. Okay. So basically they could be tangent circles, like you were saying. Display the number of seconds after which the tower will be completely filled, or invalid if the tower will never fill completely. So I don't think I know. I might try this problem at some point, even on stream. I just don't know if I'm ready for it now. But is this like a flow problem? Like, is this like network flow, or am I like way off with that? So if you can build a graph representing the relationships between the glasses and like how fast the overflow is going to happen. Not really a flow problem. So I'm trying to figure out if I go back to my handy dandy drawings. So we're gonna end up with a directed graph, and you could have, it's going to be a directed acyclic graph. You're going to have like this, and you could have this, and like, just so that it's clear that it's not a tree, like you could also have that. Well, I guess it was already clear that it wasn't a tree, but whoops. So then these edges need to contain how much of the wine from the glass above is going to accumulate below. So how would you represent that? As like a percentage, maybe? So the top glass is filled at 100 milliliters per second. Then you have to figure out intersections between circles. And so I guess what would be nice is if these, I don't know how hard, I mean, you'd have to do, like I was saying, you'd have to do math to calculate it, but if you could represent this as like a percentage, like if this was like 0.8, kind of indicating that 80% of the champagne from the glass above will trickle over and fill this one. Oh, right. You need to know when the overflows start, because once you know when they start, then it starts filling the glasses below. And then once you know that, it's kind of like does this reduce to like a shortest path? Or something like that? Once you figure all that out? not really shortest path, but it kind of reduces to like the sum of the it's like a longest path, but it's the sum of all the delays along the longest path in the tree or something like that, in the DAG. Is that right? Some of the delays along the longest path in the DAG. Is that what this is? Question mark. Whoa, why is that so big? I'm horribly sorry to derail you and run, but my friend is here. Oh, you're good, you're good. Thank you for showing me the problem. It's gonna be in the back of my mind. Maybe next time you stop by, we can talk about it. The edge weights change over time, right? Okay, it sounds really hard. Thanks for sharing though, and thanks for stopping in, and have a great dinner. Cheers. Bubbly trouble, bubbly trouble. Okay, let's get back to word search 2, because there's still more stuff that I want to do. So what's wrong with this right now? What's wrong with it seems to be that I'm generating too many of each correct answer. So the good news is I'm finding answers. My code is finding oath, my code is finding eat, but it's producing 4 of each. Why is it producing 4 of each? I remember where I was now. I was looking at eat. So there's actually multiple eats. There's eat, so there's eat going this way. There's eat going this way. There's eat going this way. So that's 3. That's 3 unique eats in the grid, and we only care about one of them. And then, but oath doesn't have that problem. Just by eyeballing this, I only see one way we can form oath. So that kind of begs the question, why are we putting it in our answer 4 times? So node terminates. Why would we get to this H tile 4 times? I'm so confused. Okay, maybe if I set a breakpoint in here, we can figure out what's going on. Okay, so if I do that for a second, we can see, oh shit, I turned off my lights. Okay. We can see the percent signs in the grid representing where we've been. So we've been at O, A at the top, then we were at the T, and then we were at the H. And so that makes sense, and it makes sense that the node terminates. So okay. So then when I hit play, do I come here again? I'm gonna hit play. What's happening here? Hold on, I'm trying to figure out what's different. Because it's basically, it looks like it's finding its way through the oath word 4 times. It's getting to that H and seeing that it terminates 4 times. But why? So I and J are 3-1. Right? And then when I hit play, I and J are 2-0. That is not right. I think I just have an order of operations problem here. Like, yeah. So when I come into this function call, this backtracking function call, I and J is the current position we're looking at, but the node represents. Okay, so actually it might be better to restructure the code so that those correspond. So let me just pass in try children of board IJ. Let me run the code. What happens now? It's not okay. Now I got no answers. So I start off at the try node for the letter, passing in all that stuff. And then we come to the top. If there's no node, we return. If the node terminates, then current word doesn't have. I see. This needs to be up here. Which means this needs to be up here. Okay, I think I'm close to being right. What's still not working here? Okay, that's a shadowed variable, which is not really great, but I don't think it's gonna make a difference. I'll call it CC anyway, though. Oh, and now this needs to be the next one right here. Okay. Okay. So that passes example test case 1, which is great. Let's use all the example test cases and run it. Okay. Now, all the strings of words are unique. Board IJ is a lowercase English letter. So what I'm trying to figure out now is what is the answer supposed to be if, like, what if oath had been in there again? So that's easy to simulate. Let's just make the last row of the first test case oath. And let's run it, and we'll see exactly whether or not we're good. We're not. So we're only supposed to keep track of, like, new words. So, okay, so I think there's an optimization here. I mentioned this before, but one thing that I could do is, instead of my answer being a vector of strings, I could change it to be a set of strings or an unordered set of strings. And then when I find duplicates, it's only going to keep one. And then before I return my answer, I just have to convert the set or the multi-set into a vector again to return it. However, I think that because we only want at most one of each input word, I think there's an optimization. The optimization is, once we find that a node terminates, we don't need to handle it again. Like, so first of all, we can do this. First of all, we can do that. But what if everything? So if we set things, every time we uncover a full word, we update the prefix tree and specify that that node doesn't terminate anymore. That works. But what if everything past that node also doesn't terminate anymore? Well, in that case, we don't need to keep any of that part of the prefix tree anymore. So let's think about this. Well, okay, so the leaves of the prefix tree are guaranteed to terminate until this happens. So kind of what I want to do, I'm trying to figure out an efficient way to do it, is like words that are lower down, like E, for example. Let's say that we're doing the traversal. We find apple. Now, because we find apple, we can actually delete. We can delete all of this from the prefix tree. As soon as we find apple, we can delete that. We don't need to consider that anymore. And then, if we find app, then we can delete. We'll be able to delete that as well. So we can delete that, and then once we delete that, as soon as we find app, we can delete this. And so the optimization is to gradually make the prefix tree smaller. I just got to figure out how to do it, and I'm going to continue to do that as I take a quick restroom break, so be right back. Aha! We're back. Also, I grabbed some nuts. Don't have any left though. Okay, let's see here. Let's see. So, I could submit this now and see if it passes. But how would I modify my prefix tree? So I'm gonna submit. Okay, so I get it accepted. I've solved this problem previously in 2020, but it's been plenty of time, so I feel good coming back today and solving it again. Now the question is, why is it so slow? 1300 milliseconds. Sheesh, it's slow, dude. So I think the optimization I was talking about, I probably am supposed to do. I just have to think of a nice way to do it. So, so I find oath, right? I find oath. Oh yeah, and I did actually, I forgot that I added this line of code, but I submitted it with this. And that's fine, that still works. But it's not as fast as it could be. Do I need to modify the shape of my prefix tree to like keep track of how many words are below each node? Like if I'm doing the algorithm and I discover that a node terminates, if I know there's no words below it, then I can delete it. How long have I been? Okay, so I want to move on to some other problems. I think my intuition for how I should go about optimizing this is right. So in this situation, I'm going to look at the solution because there's other questions that I do want to move on to. So we do get it accepted. It's just not as fast as it could be. So backtracking with try. The problem is a simplified crossword puzzle where the word solutions have been given on the board embedded with some noise letters. You need to cross them out. Yeah, this is the idea. While wandering around the board, we would stop the exploration when we know it would not lead to the discovery of new words. New words. So, once we discover a word, there's no point trying to discover that word again. So let's look at the solution. Backtracking. Okay. Okay, so here, this is a optimization. Incrementally remove leaf nodes. Can I just drop that in my code and it'll work? Like down here, like after we fully explore so if this node doesn't have any children, then we remove it. Is it that's hold on, so can I just do if not size, if not node children dot size. So we need to keep the parent nodes. Okay, so I'll just add it in here. Try node parent, and then it would be try. Pass the try in here, parent and node, and then when I backtrack here, I would pass node and node children, and then it would be like parent dot erase. Parents children dot erase. See? Whoa. What? Okay, that's not right. How did my runtime go to 2,000 milliseconds and it's still accepted? Sheesh. Okay, so what else? That's the optimization, right? If the node's children is empty, let's get rid of this and see what happens on the input. Okay, so I don't think this is working. Otherwise, I think that we would have gotten the expected output here. So the idea, I think, is that you're at a node in the tree. You explore all around with backtrack. Then you get back, so then you come out and now you've explored everything around the current tile. And so if this node doesn't have any children, then I delete this node from its parent. Oh, what about this? If I get here and there's no node, this feels right. Is this happening at all? No. Okay, so that's not happening at all. If not node.children.size. Oh wait, I need this. I think it's because of how I have my code structured. I think I need this here too. Let's make this here 0 and here 1. So if there's no node, wait, what? No. Oh, okay. And oh, we still need to return. Wait, what? Now I'm confused. What happens if I submit? Is this right? No, oh no, that's just wrong. Okay. You know, I could probably look at my code from last time, right? How did I do it last time? Okay, so this is going to be pretty similar. Okay. Okay, we do use the unordered set of string found. If the node terminates, we insert the word. Okay, we're using a slightly different approach for the coordinates. Wait, this is so weird. How is this so fast? This doesn't look like it's got any optimizations in it. Like, I'm not modifying the prefix tree. Is this what's, hold on a minute, is Let me get rid of all this code, because my other solution doesn't do this. Okay, so if I run this, it should still be right. Right, but slow. So the big difference I see between the last time I solved this and this time is that I'm just storing the word in the prefix tree. So I can do that. We can have a string word here. And then node, okay, and then node word equals word. And then I can get rid of this, and I can do, if node terminates, then push back word. That's literally, yeah, that's not faster. Why is this faster? Why is my code from 2 years ago faster when it's the same? Terminates, so I got the map, I got the insert word. Alright, I'm copying this code over, so I don't understand why it's so much faster than what I've written here. I'm calling BS. Yeah, see, it's BS. Something changed about the problem. Maybe they changed the test cases. Because I just copied supposedly my 104 millisecond solution from 2 years ago, and now it takes this long. What about this? I mean, this is just going to be a different iteration of the same, right? Yeah, this doesn't do anything significantly different. So undo, go back to the code that I wrote today. And undo these changes, because I don't think that makes a difference. What's better for you guys? Probably this, right? No, that's readable. Okay. So looking at the optimization. Optimizations. In the above implementation, we applied a few tricks to further speed up the running time. In addition to the application of the try data structure in particular, the Python implementation could run faster than 98% of the submissions. We detail the tricks as follows. One could use try simply as a dictionary to quickly find the match of words and prefixes. For example, at each step of backtracking, we start all over from the root of the try. And then, yeah. So this is what I want to read about right here. Gradually prune the nodes in the try during the backtracking. The idea is motivated by the fact that the time complexity of the overall algorithm depends on the size of the try. For a leaf node in the try, once we traverse it, i.e. find a matched word, we would no longer need to traverse again. As a result, we could prune it out from the try. Gradually, those non-leaf nodes become leaf nodes later. Okay. Yeah, so this we're doing. Alright, so I want to implement the optimization. I tried to and it didn't work. So basically, when I find a match, if I'm at a leaf, I can delete this. So if the node terminates, okay, so let's go back to passing the parent nodes through. So we pass our try here. We've got our try node star parent here. And then down here we pass, when we backtrack, node and then thing. So we got our parent. So if the node.children.size if there's no children from this node which terminates, then we delete it from the parent. Parent children dot erase C, right? And then do I need that down here too? Why is that wrong answer now? So if the node terminates, we get the word, put it in the answer, and now this node terminates if the node doesn't have children. Why we erase it from the parent? Duh. Or not? Why is that not right? Okay, let's see if it's this part that's not right. Oh, okay. I'm getting really lazy about this one. There we go. All right, I'm happy with that. So these optimizations here make my code speed up significantly faster, from like 1400 milliseconds or whatever. We even had one with 1900, 2000. And then we make those optimizations and it brings it down to like, get a couple more run times, like 460-ish through 700. Okay, so do I need, so the question is, do I need this? I'm trying to figure out if I need that. Okay, so apparently these 3 lines of code aren't necessary. So these lines of code here are basically saying, once you come out of the backtrack, if this node doesn't have any children, you can delete it from its parent. But okay, yeah, and but in order for this to speed it up, whenever we find nodes that terminate, like at the bottom of a tree, like basically the leaf nodes that terminate words, we need to delete those from their parents, and then that's what's going to reduce the sizes of those parents' children map, so that this condition can run. Okay, all right, that's it. So that is how you solve word search 2. Let me save this problem that someone in the chat threw me recently. Shit. I'll just hold on. You guys can't see because I'm just adding this to my bookmarks. Bubbly Troubly. Okay. Moving on. A couple of things left that I want to do. How long have I been live? 2 hours and 13 minutes. Stretch. Sorry, excuse me. I'm just looking at my phone for a second. Alright. So, yesterday we solved Jump Game 2. And I came up with a n-squared deep dynamic programming solution that gets accepted. Let's submit it again just to show that it gets accepted. There you go, it gets accepted. And then after I got it accepted with this n-squared DP solution, I then went and took a look at the solution tab and discovered that this can be written in linear time. And I'm going to write it that way only because there are more jump games coming up, and I want to try to make sure that I've like mastered, in quotes, like I fully understand the previous jump games before I move on to the more difficult jump games. So I remember more or less how this works. So at any point, so we're gonna have a single loop, I equals 0, I is less than n plus I. And the way you want to think about this is that at any point during this loop, you're in the middle of a jump. And the other thing is, at any point like in this loop, the jump that you're in, you're jumping as far as you possibly could have jumped when you started the jump. So that's why you have a variable which is the current jump end. And this will mirror pretty closely the solution in the solution tab because I read it just yesterday and I remember kind of what was going on in there. You also have a farthest. And so this is a minimization problem. We're trying to get to the end with the fewest number of jumps as possible. So we're going to keep track of that, all that information in ints, and we're going to return jumps at the end. So we're iterating I starting at 0 and I going to the end. Now, at any point, if I equals the current jump end, that means that when we took this jump, doesn't really matter where we took it from or how long the jump was. What matters is we took a jump at some point and we just reached the end of it. So since we just reached the end of that jump, we now need to jump again. But the other thing to keep in mind is we're not necessarily jumping from I. We're jumping from the farthest place that we know that we can jump to, which is a variable that we haven't updated yet, but we're going to update it. It's the farthest variable. So if I is the current jump end, we need to do a new jump. So plus jumps, we increase our answer, and then oh yeah, so actually we have to update farthest first. So as you're going through the loop, you're keeping track of the farthest place that you know you can jump to. So farthest is the max of farthest and nums sub I. Right. So when you're first starting, the farthest you can jump to is whatever num sub 0 is. Then once you get to index 1, which is the second position, the farthest you can go is either num sub 1 or num sub 0. So farthest is just keeping track of the farthest you know that you can jump. Also, the problem description guarantees that you can always reach the last index. So we don't have to handle the edge case where it's not possible. So as we're going through the loop, we're always in a jump, right? We're always in a jump, and we're always keeping track of. So basically, we're always like in a jump, and as we're like iterating through that jump till we get to the end of it, we're also kind of like deciding where to jump to next, and that's our farthest. Or yeah, so if I is the current jump end, then we need to do another jump. The new current jump end is the farthest that we know we can go. And then we have to update our farthest again. And what does farthest become? So we're at the jump end. So we're jumping, we're basically saying that there's another jump happening. So we're jumping from somewhere from within the last maximum distance that we could jump. And the new current jump end is farthest. Does farthest change here? Does farthest change? I think farthest is supposed to change there. We run the code, we get 3 instead of 2. Let's think about this. So jump starts off at 0. We iterate from 0 all the way through the end, keeping track of the farthest. It's the max of what farthest is currently and num sub I. Then if we reach the end of the jump, we need to we're doing a new jump. So we increase jumps. The new current jump end is farthest. Which could be like 1 away. Can't be 0 away. Because if it's 0 away, then we wouldn't be able to reach the last index. I think we have to update farthest here. And the new farthest is... So the new farthest is nums of current jump end? Is that right? I was hoping to kind of get this one relatively quickly because I thought I understood it, but I'm missing something here. Current jump end. Okay, let's debug. Let's just debug this. So let's put the breakpoint there, run the debugger. So the input is this test case 23114, and the minimum jumps to reach the last index is 2. Yeah, because you just jump to the 3 and then you jump from the 3 all the way to the 4. Wait a minute. Is the problem that we don't need to process the last index? Yeah, it is, right? Hold on a sec. I'm just being dumb, maybe? We don't need to process the last index of this array. Okay, well that is true though. Oh, no, we do need to process it because the last index could be the end of the last jump. No, it's n-1. Okay, let's run the debugger. Okay, so I is 0, n is 5, current jump end is 0, farthest is 2, because we could jump all the way to there. Step over, so jumps goes up, current jump end is 2, and then farthest becomes 1. That might not be right. Hold on, let me just get rid of shit. I'm not sure about this line of code here. Okay, run it again. Okay, so 23114 is the input. The current jump end is 0. The farthest we already know is 2 that we know so far. So we step over, we increase the jumps, and we set the current jump end to farthest. So basically we've done one jump. The farthest we can jump to is this index 1, this index 2 right here, which is a 1. So basically the idea here is we've jumped. At the farthest we can jump to is 1, but we haven't actually decided whether or not we're jumping to the 3 or the 1. But we're keeping track of what the end of the current jump is, like the maximum end of it. So this variable, current jump end, should probably be called max current jump end. I actually like that as a rename because it's not the actual end of the jump. what it represents is the maximum possible end of the current jump. The point at which you have to have started another jump. That's what this variable represents. So let's debug again. Okay, right, so we're here again. We increase the jumps, and then our max current jump end is 2, because we're either going to here or we're going to here. Step over. Now we come back in. We're at the next index. We're at index I equals 1. So we're looking at the 3, and farthest is, oh, no. Oh, okay. So farthest, I am calculating here that farthest is 3. That's not correct. Farthest is the index, is the value with the current index plus the current index. So that's just a silly mistake. So it's I plus nums of I. I could run the program right now, but I want to keep debugging so I can step through it and explain what's happening, both to anyone who's watching and to myself. So we're at the beginning. The farthest we can go, because we're at index 0, I equals 0, is 2. And then we have to do a new jump, so the max current jump end becomes 2. Then we come back around, we're looking at I equals 1, where there's a 3 there. So we update the farthest to be 4. 0, 1, 2, 3, 4. Yes, exactly. So basically, we now know that if we were, so right now we're in a jump, and we know that from somewhere within the current jump, we land, and we know that we can jump at least all the way to index 4, which in the case of this test case is the answer. But let's keep going. So we didn't hit the end of our current jump, so we go back around. We're looking at farthest. We're looking at index 2, so farthest is not going to change. Farthest is still going to be 4. However, now we are at the end of the jump. So we jumped from the starting point, we jumped from index 0, and we landed either at the 3 or at the 1. It doesn't matter where we landed, we know that we've landed. So we then have to increase our number of jumps, and the new max jump end is farthest. So now so basically, having jumped from either of these two positions, we could get to the 4, but not either, but somewhere within this range, we knew that we could jump to the 4, and in this case, it's the 3 that enables us to get there. So then we come back around. Farthest is not going to change. That's for I equals 3. Next, now we come back into the loop. Oh, okay. Yeah. So because I updated my loop end condition so that it doesn't include the last index. Then is that right? Do I need to process the last index? I don't know. Okay, so for that part, I'm not sure. Let's just run it and submit it. Okay, so that's right. So I solved, like I said, I solved this problem, Jump Game 2, yesterday, and I solved it using an n-squared algorithm. So my runtime was ranging from 400 to 760. Then I went and read the solution and discovered the way to implement it in linear time, and so I just did that. So this is the linear time solution to Jump Game 2. Many more jump games to come. Not sure I'm going to look at those right now. Let me try to think here. Let's go take a look at... Let's go here. Let's look at this DP study plan. So I did do an actual interview today before the stream. So I might end a little earlier today. and just kind of relax, probably play some video games. But before I commit to ending the stream, let me just read this problem description and see what it's about. So, you're given an m by n binary matrix grid where 1 represents land and 0 represents water. We're familiar with that concept. I've solved several problems that use that on stream. An island is a maximal 4-directionally connected group of ones. The grid is said to be connected if we have exactly one island, otherwise it's said disconnected. In one day, we are allowed to change any single land cell into a water cell. Return the number of days to disconnect the grid. The minimum number of days. Interesting. So basically, we want to create at least 2 islands. Right? Your grid could start off with 2 or more islands, in which case the minimum number of days is 0. But I'm assuming that most of the interesting inputs to the problem have the island to be connected at first. And so you need to figure out how to disconnect it. So, and you can disconnect a single island into 2 islands, 1 cell at a time. And so essentially this problem reduces to how many cells do you need to remove minimally to disconnect an island? How do you know even where to start? I don't think I know the know-how for this one. Let's look at some hints. Okay, so obviously we return 0 if the grid is already disconnected. Return 1 if changing a single land to water disconnects the island. Okay, got that. Otherwise return 2. Wait, what? Otherwise, return 2, we can disconnect the grid within at most 2 days? What? Hold on. You're given an m by n binary grid where 1 represents land and 0 represents water. An island is a maximal 4-directionally connected group of ones. Maximal 4-directionally connected group of ones. What does that mean? It's what does that mean? So that honestly the problem description is not very good. So I think what they're getting at is that if you have like 1 1 1 1 1 1 1 1, like let's say that you have this island, right? I think what they're saying is that replacing these middle 2 ones with 2 zeros disconnects the island. Because it's no longer maximally 4-directionally connected. Not a great problem description. So, okay, what are the related topics? Depth first, breadth first, matrix, strongly connected components. Okay. So if it's already disconnected, you just return 0. Then the next thing to check is there anywhere where a single land disconnects the island? Okay, I'm not a big fan of this problem. Python, you need it most 2 days. Okay, let's just see what people are saying. Day 0, check island. Day 0, return 0 if you have less than or greater than 1 island. Try to add water at any given location. Check if that gives you valid island formation. Otherwise, just return to. So, okay, let's read this first part. The tricky part of this question is to notice that you can disconnect any given island formation in at most 2 days. And you need to convince yourself that this is true. Example, imagine we have a 30 by 30 array of all ones. For the top left corner, just remove the one to the right and below. Oh. Got it. Okay. So this is not right. This is not what they're saying at all. What they're saying is that if you have this island, then in at most 2 days, you can turn it into this island. And now you've disconnected the top right corner. I understand. Okay. That's enough of that one. So, okay, let's have a look. Let's just have a look at the maximum subarray. Given an integer array nums, find the contiguous subarray containing at least one number which has the largest sum. A subarray is a contiguous part of an array. Is this sliding window? Okay, so apparently you solved this in linear time using dynamic programming. So int n equals nums.size, and then you'd have vector of int dp containing n things, and we want to figure out what dp of I is. So dp of I would be something like max contiguous. Subarrays are contiguous by definition. Max subarray, maybe max subarray ending at I. So sum of max sum subarray ending at I. Is that right? Is that correct? Not gonna lie, getting a little hungry, which is a problem because I don't have any food. So So dp of I, how do we calculate dp of I with respect to dp of I minus 1? So dp of I minus 1 it would be the max of dp of I. Oh no, it would be the max of nums I and nums I plus dp of I minus 1. And then answer is the max of answer and dp of all I. So is that right? dp of I is the sum of the maximum sum subarray ending at I. And so then the way you would calculate that is dp of I is going to be the max of just nums I by itself, or nums I plus the dp plus nums I plus the maximum of the subarray ending at the previous one. This seems right. Am I missing something obvious here? Why don't I just code this up? Because this is not particularly hard to code, so we'll know very soon if this is wrong. So I equals 1, I is less than n plus I. We need base cases. So we need our vector. Oh, I already have it. So dp of 0
let's bring that beat down.
Equals nums 0. Then dp of I is the max of nums I and dp of I minus 1 plus nums I. And then the answer, we need to keep track of our answer. Answer is just, can start off as nums of 0 as well. Answer is the max of answer and dp of I. And then return answer. Is this like a... It's been a while since I've done problems like this. Wrong answer or correct? Okay, so we get the right output for this. What I'm trying to remember is this like a really famous problem where the solution is like named? Let's submit. Okay, so we submit and we get, we do get accepted on the first try, which is POG. Faster than 75%. Memory is not great, so I think that I'll actually, I don't do this every time, but I might go through and improve the memory usage of this. Also, look at all the recommended problems. LeetCode's like, man, you solved that? Check out all of these. And also, it's a little slow. Why is it? Well, it's probably just slow because of the extra memory. So what was I trying to think about? There's like a name of like a historical computer scientist who I think is the one who's credited with this algorithm right here. So I think I can probably get the name just by searching this text in Google. Yes, yeah. It's Kadane's algorithm. That's the name I was trying to remember. Kadane algorithm. So Kadane's algorithm is a famous algorithm for solving this problem. The max subarray problem, where you just you represent it this way. dp of I is the sum. It's the sum of the maximum sum subarray that ends at I. And then if you structure it that way, then you can calculate dp of I just by looking at nums_i and the previous elements of the dp array, which is the sum of the maximum subarray ending at I minus 1. So dp of I is either it's just nums of I, or it's nums of I plus. So basically you're saying nums of I is either going to be the start of a new subarray with a hopefully a better sum, or you're going to add nums of I onto the end of the previous subarray. And so that's this max right here decides which of those two things you do. And then you're keeping track of the answer along the way. So you always just check to see if the maximum sum of subarray ending at I is just the maximum sum you can find overall. So if you look at Kadane's algorithm, scroll down and find the code. Yeah. So, okay. So I just cheated a little bit. I just saw. So the idea is that you're keeping track of a local max and a global max. And so I'll rewrite my program that way now. So you don't need the DP. All you need is the local max, which is the max of the current subarray that you're in, and then the global max, which is the final answer that you return from the end of the program. So we can do it that way. So local max starts off at nums 0, and global max also starts off the same way, like that. Now what you end up returning is the global max. And let me rewrite this part here. So at each iteration of the loop, at each index, you check to see, you update the local max, and it's the same way that I was doing it before. Either the local max is just nums sub I, and that means you're starting a new subarray, or local max it keeps like its previous value, which means that you're just adding I onto the end of the previous subarray. So local max is going to be equal to the max of nums sub I and local max plus nums sub I. And then global max is equal to the max of global max and local max. Submit. Okay, so that improves our memory footprint. Now our memory is less than 90% of other submissions. The time, so this is kind of weird and also slightly annoying. Like, I solved this problem back in 2020, and my times were less. And so I think what probably happened is they changed like the input data of the problem a little bit, like probably made it a little bit bigger. Also my code was written in JavaScript back then, but we can see what the code was, and it's going to be the same thing. Oh wait, that's the divide and conquer approach. Oh, okay, here we go. So this is the Kadane's algorithm, and then it looks like I decided to implement the divide and conquer approach. So for divide and conquer, let's see. It's probably n log n, right? Well, you know what? I'm not gonna figure it out right now. There's something else I wanted to look at. So I'm just gonna go ahead and check this out. So optimize brute force. So that's n squared, that doesn't work. Dynamic programming, Cadane's algorithm. So here's the same code where it runs in linear time and constant space. And then approach 3 is advanced, divide and conquer. And let's just look at the intuition real quick. So the approach is slower than the second approach and uses more space, but it's still a nice and different way to approach the problem. Yeah, because I think this is going to end up being n log n. A lot of times divide and conquer algorithms where you're like splitting up things in half over and over again, a lot of times those end up running in n log n time. Prime example of that is pretty much most sorting algorithms that are optimized, like most fast sorting algorithms, not including bubble sort and shit like that, but you know, I'm talking about like quick sort and merge sort and those types of sorts. Those are all divide and conquer, and they all run in n log n time. So the approach is slower. Alternative ways to solve the problem. Divide and conquer is an extremely common type of algorithm. This solution recursion. Yeah. Divide and conquer algorithms involve splitting up the input into smaller chunks until they're small enough to be easily solved, and then combining the solutions to get the final overall solution. If we were to split our input in half and then logically the optimal subarray either uses elements only from the left side, only from the right side, or uses a combination of elements, which means it would cross the midpoint between those. Thus, the answer is simply the largest of the maximum subarray contained only in the left side, the maximum subarray contained only in the right side, and the maximum subarray that crosses between them. Maybe I do want to code that up. That seems fun, but we can just go down here and I'll skip the code, and this is just what I wanted to show, which is that your time complexity increases to n log n, and then your space complexity increases to log n, and I assume that's because of, yes, the recursion stack. Yeah, yep. Someone says, how is this easy? It's not anymore, right? Did they change the difficulty? They made it medium. Yeah, they made it medium. Okay, so I might come back and solve this one using divide and conquer. I think that would be a good exercise. But what I wanted to do right now is, well, actually, I'm trying to decide if I even want to do it. But I wanted to look at strongly connected components. And I wanted to look at a problem that uses them to get a fast solution. So just give me a sec here. One sec. I'll be back momentarily. Okay. So I've solved this problem before, but I like it and I want to solve it again. It's called airport connections. Okay, and this right here is AlgoExpert. This is a great tool for interview preparation. So is that zoomed in enough for the stream? Okay, we'll do it like that. And so let's look at the problem description. Hold on, before that, I'm just gonna go grab some water. One segundo. This will be the last problem I do today, but It's been a while since I've done anything related to strongly connected components, so I want to review this concept. But I'll be right back for a second. Okay, so trying to decide, how do I do this first? Do I go over the problem description, or do I tell you about strongly connected components first? Let's go over the problem description. Okay, so you are given a list of airports, 3-letter codes like JFK, a list of routes which are one-way flights from one airport to another, for example, JFK to SFO, and the task write a function that returns the minimum number of airport connections that need to be added in order for someone to be able to reach any airport in the list, starting at the starting airport. Note that routes only allow you to fly in one direction. For instance, JFK to SFO only allows you to fly from JFK. So we're already talking, you can tell that we're talking about a directed graph. Also note that the connections don't have to be direct. It's okay if an airport can only be reached from the starting airport by stopping at other airports first. Right. Okay, so let's switch over to the drawing tool, and let's look at the problem description in a visual way. So basically what they give us is they give us a bunch of airports, right? So I'm just going to draw a bunch of nodes. This is going to be a directed graph, so I'm going to add edges between these. But they give us a bunch of airports like this. And they also give us a starting airport. So let's change the background of the starting airport. Bro, I don't even know. There we go. So this orange one is the starting airport. Now, these airports have flights between them. So it could be like this. It could be like that. You could have something like this, like that, like that. Now, right now, it looks like I'm making a DAG, but this doesn't have to be a DAG, okay? So, for example, this could go right here. Also, this could go right here. This could, so this right here could fly back here. So the only requirement is that this is a directed graph. This airport could potentially fly right here. Let's have an edge here. Okay. Let's have an edge from the starting airport. Okay. Let me just look at this, see what we're looking at. Okay. Yes, so now the question is, the question is, now that you get a graph, you get routes, which are directed edges in the graph. Return the minimum number of airport connections that need to be added in order for someone to be able to reach any airport in the list, starting at the starting airport. So it's always starting here at the starting airport. Okay, now I want to talk about what a connected component of a graph is. So connected components solves this problem really nicely. And the way that it does it is, so essentially a connected component of a graph, of a directed graph, is, or even a, so in a undirected graph, a connected component is just a group of nodes that are all connected to each other. That's the components of the graph. In a directed graph, you have a concept called a strongly connected component, which is a subset of nodes such that every single node in the subset can reach every other node in the subset. So we already have some connected components here. Like this component, for example, is connected. That component is connected. Let's hold on a sec. Let's move this out of the way for a second. We have more connected components. This component right here, this is a strongly connected component. Everything, all three of those nodes can reach all the other nodes. And you can tell that that's the case because of the cycle, right? There's a cycle if you follow these edges around this way. Similarly, in this strongly connected component, there's also a cycle. Hold on a sec. Let me move this over. And then I think that's it. So, well, there's more strongly connected components, but the idea is that all these nodes that don't form cycles with other nodes, these are all their own strongly connected component. So that's a strongly connected component. That's a strongly connected component, and the starting node too is also a strongly connected component. And then don't forget down here, these two nodes are part of the graph, but they're not reachable from any other node in the graph, but they are reachable from each other, which is why they have their own strongly connected component. So the cool thing about strongly connected components is once you take a directed graph and you find the strongly connected components in the graph, you actually have reduced the graph to a directed acyclic graph. So and you want to, instead of thinking about the original nodes, you want to think about the components themselves. So like there's one edge going from the starting node to this strongly connected component, and because it doesn't really matter which node this edge is going to, because every single node in the strongly connected component can reach every other node because there's a cycle. So really this strongly connected component over here just has an edge to this strongly connected component here, and then it's the same for all the rest of them. This strongly connected component has an edge to this one to this one, this one to this one, this one to this one, so on and so forth. So right now, so if we go back to the question for a second, airport connections, and what we're trying to do is figure out the minimum number of airport connections that are needed to be added in order for someone to be able to reach any airport starting from the starting airport. So because we've reduced the graph down from a normal directed graph to a directed acyclic graph of strongly connected components, you don't have to look too hard to see that all of these nodes here that are part of the DAG connected to the starting node, they're all already reachable from the starting node. So all these nodes right over here, no connections need to be added for the starting node to be able to reach them, because let's say we want to get to this one down here. We can go from the starting node into this strongly connected component. Then there's an edge down here, right? You know, you could, it doesn't really matter. You can go around in circles a couple of times, but you'll still be able to come down here. Similarly, if we want to get all the way to this node over here, it'll go bloop, bloop, bloop. So anyway, the only problem, so the thing now is, there are nodes though that are unreachable from the starting node, and it's going to be the strongly connected components that are not reachable from the starting node. Yeah, so in the case of this example that I drew out, you end up needing to add an edge either here or here. Like an edge to either of those would make every single node in the graph reachable from the starting node. Ooh, look at that. So the first thing that we're going to do in the solution to the problem is we're going to write some code that goes through the DAG that we get and turns it into it goes through the graph that we get and turns it into a DAG of strongly connected components. Once we have that, the question reduces to how many of those strongly connected components in the DAG are not reachable from the starting node. So then how do we get from that to an answer? That's what I'm trying to figure out. That's what I'm trying to figure out. Also, I've solved this problem before. It's been a while, but I've solved it before, which is why I know I like it. It's why I know I like the solution. Well, I'm trying to recall the exact way that you get from figuring all this out to having a answer. Okay. So let's move all of this in a little closer. And so what you get here, let me just draw this out again. So let me change the color to blue. And so this, let me move this over here. This is the strongly connected component graph that we just made. So we have, blue means strongly connected component. So this is the starting node. And I missed a node. Okay, and this goes down here. So these are the same graph, except here we can see the original nodes over here we can see the DAG of strongly connected components. So once we have the DAG, let's go ahead and make this guy orange as well, because that's the SCC that corresponds to the starting node. I missed an edge, so there is an edge here as well. Yeah. So once we generate our strongly connected component graph, the task then is to find the minimum number of airport connections that need to be added for someone to be able to reach any airport. And so the problem is reduced. Once you make the strongly connected component graph, the problem is reduced to how many strongly connected components are not reachable from the strongly connected component containing the start node. So 1. So is that maybe that's how you generate the answer. You iterate through the strongly connected components, or you can like DFS the strongly connected component graph, right? You can start at the start node, and you can go through, and any node, any SCCs that you don't reach need a connection added to them. So like we need a connection here. Also, if there was another disconnected, strongly connected component, like let's say that we had, here, let me add some more stuff. So let's say that we have 3 strongly connected components and an edge between 2 of them. So we also need to reflect that over here, unfortunately. So we need another node down here, and another node over here. And then we need... So you have those, and then we have an edge here. Okay. Okay, so now we've got that. Let's think about this. So all of these, this whole DAG that is reachable from the starting node is good. It's these 3 strongly connected components down here, which are these 3 over here, that we need to worry about. So this one right here needs its own edge. Let me change the color to, I don't know, red. So like, we need an edge here, and we need an edge here. But the nice thing is about this, like, there's a bunch of edges that work, right? So those 2 edges could be the answer. Also, like, these 2 edges could be the answer. But the fact of the matter is, no matter how you do it, you need 2. You need 2 edges between the SCCs to be able to connect it. So how do we generate an answer? Do we iterate through all of the strongly connected components and we count the ones that do not have an incoming edge? Is that it? Except for the starting node. We don't care about the starting node. So every single one of these nodes here has an incoming edge. This node has an incoming edge, but this node does not have an incoming edge, so there's no way for the starting node to possibly get to it. This node does not have an incoming edge either. So yeah, I think that's the answer. So the solution to the problem, I believe, is to generate your strongly connected component graph, directed acyclic graph, and then you count the number of strongly connected components that do not have that are not the strongly connected component containing the start node, and also they do not have an incoming edge from another strongly connected component. If they do not have an incoming edge, then we need an edge to them in order for the starting node to be able to get there. And as I mentioned before, there's a bunch of different edges you could do. So if you wanted to, you could put an edge here, and you could put an edge here, like that, that would work. There's an infinite number of different ways to do it. You could put an edge here. Oops. Still getting used to the drawing software. You put an edge here, right? Just the fact of the matter is there's 2 strongly connected components that don't have incoming edges. Okay, so I think that solves the problem. I'm gonna go ahead and try to implement it that way, which takes us to the next interesting part of the stream, which is where I remind myself how to take a graph, a directed graph, and reduce it into the strongly connected components of the graph. So let's go back to airport connections and try it. Okay, so let's first things first. Let's process the input. Here we go. You know, I had a solution here. I'm just going to undo until it comes back. Okay. So as input, you get a vector of the airports. You get a vector of string. You get the routes, and you get the start. So I think the first thing to do here is to process this into something nicer. So let's make sure we know how to get the index of each airport. So, well, first of all, n, or in the case of graph theory, we should call it v. V is going to be airports.size. That v is the number of vertices, and e is the number of edges. I don't actually know if we need that information, but the next thing is let's make it possible to map from the airport name to its index. airport to index for int I equals 0, I is less than v. Okay, so this should be little v plus plus v, and then airport to index sub airports v equals v, so we get that. Now let's create the graph, and in this case let's create it as an adjacency matrix. So we're gonna make a graph. So it's gonna be a vector of int g, but no, we'll just call it adj, which is short for adjacency list. And it needs to have v. I don't know, I really want to call this n. Should I call it v though? Who knows, dude, who knows? Technically v is the set of vertices, not the number. It's the number of vertices would be the magnitude of v. But let's go with this for now. Hopefully I don't get too confused. So let's go for auto routes in the routes. So this is where we're going to get a UV. So string u equals route 0, and string v equals route 1. And now we insert it into the adjacency list. So adjacent, oh, and we need to get the index. So that's why I made this map here. Just like that. Then adjacency list of u dot pushback v. Okay, does the code run? No, the code does not run. Why? Const char. What happened? Give me a line of code, dude. Oh, line 12? What's wrong with line 12? Oh, do I need to import? Map. No viable conversion from unordered map. Oh, yeah. These become ints. Okay, so the code runs. We failed the test cases, but just wanted to see that the code runs. Okay, so this is where it gets confusing. Well, not confusing, but this is where more explanation is needed. In addition to an adjacency list, I need a reverse adjacency list, which is going to represent the exact same graph, just with every single edge flipped in the other direction. And I'll explain in a minute why I need that. So the reverse adjacency list would have an edge that goes from V to U. Like that. Okay, so the next step is generate Here, let me just add some comments. Generate the
According to Wikipedia,
Alexa,
Gemini is the third aspect.
stop. Generate the strongly connected components. Then once we have it, count in degree of each SCC. So we'll abbreviate these to SCCs. Count in degree of each SCC that does not contain the origin. Origin here, origin airport. Yeah, let's do it this way. Let's leave that as starting airport, and then we'll have int origin equals. Hold on, this needs to wait though. So after I do that, int origin is going to be airport to index of starting airport. Okay. Count in degree of each SCC. Then the answer equals number of SCCs. Number of counted SCCs with in degree 0. In degree simply meaning the number of incoming edges from other strongly connected components. I've been talking about strongly connected components over here, so I can go back and look at it if anyone wants me to. Okay. And also, yeah, this is airport connections from AlgoExpert. So what's next? So I made an adjacency list, and I made a reverse adjacency list. And now I'm going to generate the strongly connected components. And I'm going to do it using, let me see if I can spell this right. Kosaraju's algorithm. So that's what we're going to do. So I've written this algorithm before. I used to have it memorized. It's been a long time. I don't have it memorized now. I'm going to review it. Then we're going to code it up. And then we're going to use the output of the algorithm to generate a answer to the problem. As I have described in the comments, the next comments. So that's the reason I made a reverse adjacency list, is because Kosaraju's algorithm utilizes a reverse adjacency list of the input graph to generate the strongly connected components. Okay. So here's the algorithm. Do a DFS on the original graph. Keep track of the finish times of each node. This can be done using a stack. When a DFS finishes, put the source vertex on the stack. This way the node with the highest finishing time will be on top of the stack. Okay, I vaguely recall needing to do that. So there's going to be two DFSs. So I'm going to have void DFS1, which is going to have code in it, and void DFS2. The first DFS operates on the original graph. So we get a vector of int adjacency list, and we get a node int u, and we get a stack of int order, and so at the end of the at the bottom of the DFS1 function, we push the node order dot push u. This is a, so we do need to keep track of visited as well. So I think we need a visited, I think we need a vector of int of bool visited of size v, where everything starts off as false. So we're gonna, so Kosurju's algorithm, we have the first DFS on the original adjacency list. We need to DFS from every node though. So for int u equals 0, u is less than v. This is why it's confusing. I don't like how I used v for what I would usually call n. So I'm going to rename it now. And we also don't need the number of routes. So let's delete that. The number of nodes in the graph, I'm just going to call n. So all of these need to be n, and that needs to be n. And then I can call then I can call this u, because u is pretty common in graph theory to just refer to a node in the graph. And then if you're talking about like two nodes at the same time, or perhaps a node that has an edge to another node, then uv is very common. So u is less than n. Yeah, like this for example. We iterate through all of the edges, and we know that there's an edge from u to v, so adjacency list u push back v, reverse adjacency list v push back u. We create this visited thing, which is false. Everything's false. So we put our adjacency list, our visited, the starting vertex, and then also the order. So that's the other thing we need, is we do need a stack as well. So we need a stack of int, and this is the order that we're going to generate. We'll have order and we'll have u. Okay, so we have something like that. We need to import. We need to include stack, since we're using a stack now. We don't actually need this if statement here. We can put it inside the DFS. Oh, but we do need to. So what order am I passing shit in? Adjacency list, visited, order, u. So this would be the vector of bool visited. Bloop, like that. And then we'll have int u at the end. And then if visited u, we return. Otherwise, we visit u. Visited u is true. Then we go through all of its children. So for int v in the adjacency list of u, DFS again. So adjacency list, visited, stack v. Is that it? That might be it for the first DFS. What happens if I run the code? N here. Oh. Order. Right here. Okay, so that's the first DFS for Kosaraju's. Then, well, the output of that is that we get the order. Now we need to unvisit everything. How do I fill a vector in C++? It takes, okay. I mean, that's fine. So we'll include algorithm, which I'm pretty sure has the fill function. So then after we do that, we would fill visited.begin through visited.end with false. So we're going to DFS again, but now we're DFSing the reverse adjacency list. And we're also, we need now a new array. And so the way that Kosaraju's algorithm outputs the strongly connected components is it gives you an array. The output of the algorithm is an array where every single strongly connected component gets assigned a representative. And so the array would basically indicate what the representative node is for every SCC. And that's actually similar to union find, how every single component has a representative. Okay, so now we DFS the reverse graph with the source vertex as the vertex on top of the stack. When the DFS finishes, all nodes visited will form one strongly connected component. If any more nodes remain unvisited, this means there are more, so pop vertices from top of the stack until an unvisited node is found. This will have the highest finishing time. Yeah, okay, I understand. So we do need to create our SCC. So vector of int, and we can call it parent. We could call it SCC parent. I don't know why, but I've seen implementations that call it who, and I kind of like that, so so I'm calling it who as well. And now for okay, so while the stack has stuff left in it, so while not order dot empty, we DFS. DFS2, and we pass in our reverse adjacency list. Visited. Who? And order dot pop. Stack.pop returns the thing, right? C++ stack pop. It's void. Oh man, make me. Okay, so what we want is top. We want what's on top of the stack, and then we need to pop. So it's gonna be order.top. That fourth parameter is the representative of the SCC. Order.pop. Okay, so let's implement it. DFS2, so it takes a lot of this same stuff. And we can call this int, we can call like rep, like representative. You can call it root. I'm gonna call it root. And then instead of adjacency visited and order, you get the vector of int who. So now, if it's visited, we leave. So this is similar to the last one. If visited, oh, and we need you and we need root. So we also need like the current node that we're at, and then root represents the representative of the current strongly connected component. So there, that fixes that. So now if we're visited you, we return. Otherwise, visited you is true. Who of you equals root. And then for int v of, and then this time it's the reverse adjacency list. So int v of the reverse adjacency list of you, dfs2 raj visited who, root, and v. Does the code run? The code runs. Let me just make sure that that's right. So you do the DFS again on the reverse adjacency list. Pop in from the stack until an unvisited node is found. Okay. All right. Okay, so I think that logic is right. So assuming that it is, we can proceed with the code, with the rest of the solution, where we now want to check the in degree of all the strongly connected components that are not a strongly connected component that contains the origin. I love strongly connected components, dude. I wish there were more LeetCode questions that used them, but I think they're considered a fairly advanced concept. Like, it's unlikely that you would need this in an interview, or, you know, it's unlikely you would need this outside of the competitive programming scene. So we need to know what the in degrees are. Vector of int in degree of size n. So the interesting thing now is, even though we still have n nodes in the graph, there's way fewer that we actually care about. We actually only care about nodes where who of you equals you, because we're going to use those nodes as the nodes in the directed acyclic graph of strongly connected components. So we really only care about nodes where who of you equals you. But since we don't know exactly how many of those are, it's easier just to keep everything kind of the same. So we have in degree, and we start off all the in degrees at 0. And now what we're going to do is we're just going to go through the whole adjacency list of the graph, and we're going to figure out the in degrees of the strongly connected components. So for int u is 0, u is less than n plus plus u, and then for int v in the adjacency list of u. So now we know there's an edge from u to v. So if u and v are in the same strongly connected component, then it doesn't matter. We actually already know that those nodes are reachable from each other. So we need to make sure that u and v are in different strongly connected components, And the way we do that is if who of u is equal to who of v, then we can continue, because that just means that this specific edge u and v is within a strongly connected component. We don't care about that. We want to know about edges that cross strongly connected components. So we get down here, and now we know that this edge crosses the boundaries of strongly connected components. So we need to increase the in degree of strongly connected component containing v. So in degree, so we're going to do plus plus in degree of who of v. Is that right? So basically we're going to get the representative of the strongly connected component containing v. We increase its in degree. But okay, yeah, that's right. So after we calculate that, now we can figure out our answer. So answer is 0, and we return the answer. And so now we're going to go through all of the nodes. We're going to go through all the strongly connected components one at a time. And if their in degree is 0 and they also don't contain the origin, then our answer increases by 1, because we were talking about this earlier, but that means that we need to draw an edge to that strongly connected component. We could draw the edge from anywhere. These two red lines are just examples of where the edges could be drawn, but the fact of the matter is, because the in degree is 0, we do need an edge there. We do need an edge to it. So for int u is 0, u is less than n, plus plus u. If who of u is not equal to u, continue. So we only care about the in degrees of the strongly connected components, and that's actually also the only in degrees that we even kept track of. So we need those to be equal. Now, if let me just write this in a straightforward way, even though you could obviously combine some of these conditions and stuff like that. We also don't care about we don't care about the SCC that contains the origin. So if u equals origin, continue. Okay, cool. Like I said, we can combine some of these conditions together, but I'm just trying to write it as I'm explaining it. Then the next thing that we need to do is increase the answer if the in degree is 0. So if the in degree of this strongly connected component, if it's 0, then we increase the answer. Okay, cool. So we're getting some past test cases. It looks like something is still wrong. Man, raw output just makes it look like everything's wrong. But I don't know, AlgoExpert, help me out here with your UI. Custom output is way better. Okay, so test case 6 failed. Expected output 10, I said 11. Test case 7 failed. I said it's supposed to be 3, but I said 4. Test case 12 failed. Okay. So it looks like for the test cases that I'm failing, I'm actually outputting 1 more than I should be. Oh, wait. Yeah, we're overcounting because multiple nodes that exist within the same strongly connected component, we don't want to count that in degree of that twice. So we could, this is kind of a naughty way to just count it once. Like we don't need in degree anymore after this. So in degree oh wait, no, this isn't it, right? That's not what the problem is. No, that's not it. That's not it. That was just me being silly. Something else is wrong. Something else is wrong, and I'm gonna brainstorm what it could possibly be, because quite frankly, there's a bunch of odd possibilities. I'm gonna brainstorm what could be wrong while I take a quick bathroom break. So I will be right back. What is wrong with the code? What is wrong with the code? Someone tell me what line of code it is. So in the cases that I'm getting the wrong answer, I'm overcounting. So let's look at this. If who of you equals who of v, then u and v are in the same component. Do nothing. Otherwise, increase the in degree of who of v. Then we come down here, and we're trying to count the SCCs that have in degree 0. Who of you needs to be equal to you? Oh wait, this is the problem. If who of origin equals u, okay, that's what the problem was. So the idea was right, but the implementation was wrong. Like, we don't want to count in degree 0 for the strongly connected component containing the origin. So we figure out the parent, like we figure out the representative of the strongly connected component containing the origin. And if that's U, we continue. And we already know U is its own representative, because otherwise we would have continued here. So let's submit. Cool. So we get all the test cases. So this is my second time solving this on AlgoExpert. I solved it probably about 2 years ago, and so my solution 1 I expect was fairly similar. Yep, looks about the same to me. Let's take a look at their solutions. Solutions. They only have one example solution. Oh my god, dude. How am I supposed to read this? So the time complexity of this approach is linear, because Koresaju's algorithm runs in linear time. So if we see what we're doing here, for loop over n, for loop over edges. So it's I mean, the time complexity is just v plus e. Then for the DFS, we're visiting every node once. So it's linear. Then for DFS2, we're also visiting every node once, which is linear. Then we iterate through all the nodes and their edges. So this is going to be V, and then this is just sorry, this is E, and then this is V again. So what we end up with is this is just O of V plus E. What do they get? So let's look at their time complexities. A times log of A. So A is just V. So it's V times log V plus E. Then mark unreachable connections is V times V plus E. So that's we're already on the order of V squared there. Get unreachable airport nodes is V plus E. But that's not the whole solution though. This is just part of the solution. So what they've done here is every single function that does like a meaningful piece of the of solving the problem, they've put the time complexity, and then for the overall function, which is the airport connections function, they've just added all of that together. So let's see if we can follow the logic here. So they create their airport graph, which is a map from string to airport node. Then they get the unreachable airport nodes, mark unreachable connections, and then they get the minimum number of new connections. Well, how do they get the minimum number of new connections? Let's look at this. So they sort the unreachable airport nodes, and then they sort them with a custom sort function, which is they sort them by unreachable connections. I don't know. I understand that this problem has been on AlgoExpert for a long time. but they do need to include a strongly connected component solution in the example solutions, I think. Let's look at the hints. Start by creating a graph out of the inputs. Each airport should be a vertex in the graph, and each route should be an edge. The graph should be directed with potential cycles, and since it's possible for there to be round-trip flights between airports, or for some series of flights to eventually lead back to an arbitrary starting point, how can the graph be useful? Yeah, so you're basically, there's going to be DFSs. Using the graph mentioned in hint 1, try getting all of the airports that are reachable from the starting airport. This can be done using depth-first search. Is the number of unreachable airports the answer? No. Once you have the number of unreachable airports, yo, what's up, Tardsky operator? I feel bad, but you're kind of coming in on the tail end of the stream. I solved several LeetCode problems, and then I just wanted to do this AlgoExpert problem. But yeah, I paid for it just for a year, because I'm not sure how long my job search is going to take. But I've paid for it before, and I've gone through all of their content, and in my personal opinion, it's extremely worth it. You said you're thinking about it, was also considering algo.monster, and there's also paying for LeetCode Premium. Yeah. Well, the nice thing is LeetCode Premium is just monthly, so you could end up only spending like 10 or 20 bucks if you get your job within 2 months. But then, you know, AlgoExpert, even if it only takes you a month or two to get the job, you have the platform for a year. I don't know what algo.monster is though. Let's see. Master the coding interview without the endless grind. Algo Monster will help you crush the technical interview. Okay, so what do they offer? Learn the patterns. Select a topic to explore. Oh, that's cool. Yeah, I like their topics. Dynamic programming, heaps and priority queues, graphs, backtracking, binary search, and top 5. What is this? Top patterns to conquer the technical interview. DFS, basic programming, 2 pointers. Oh, that's interesting. They have it like broken up by employer too. So what is Amazon? What is Amazon like? Apparently Amazon's one of their biggest things is DFS, then BFS, then basic programming. Greedy hash heap seems to be really big. Also try, not surprisingly, they like tries and 2 pointers. This is a right here, this monotone stack. That's actually something I need to review. Does anyone else ask that? I don't see monotone stack under any of the other pie charts. Okay, so I need to study monotone stack. LeetCode monotone stack. 1 fee of 75. Yeah, honestly, I can't comment on Algo Monster. Don't know anything about it. If you have other people whose opinion you trust who recommend it, then yeah, maybe it could be worth it. But yeah, as I said, I paid for AlgoExpert, so I'm definitely going to be focusing on that. Okay, so monotonic stack. So I'm going to have to look at some of these, probably tomorrow though. Let's see. So we solved that one. I wanted to look at the rest of. I wanted to look at the rest of these hints. A single unreachable airport could have connections to a bunch of other unreachable airports, potentially making it more valuable since adding one connection to it would make the other airports reachable. Yep. Calculate the number of... So then they go on to just give their solution in word form. And the unfortunate thing is, like, this is a really great problem, but the optimal solution uses strongly connected components. And when you use those, you get the running time of O of V plus E. which is way better than this. A times A plus R plus A plus R plus A log A. Also, thanks for hopping in. Thanks for coming back to the stream. I do recognize your username from the other day. So the thing about strongly connected components, though, is it's not likely that that they'll ask a question that really needs it in an interview. I kind of wish they did, because I know how to do it. And it'd be like an easy way to like get a quick pass on an interview. Let's see, next greater element sub I. Apparently this is a monotonic stack problem. The next greater element of some element x is the first greater element that is to the right in the same array. You're given two distinct zero indexed integer arrays, nums1 and nums2, where nums1 is a subset of nums2. For each I is between 0 and num's length, find the index j such that nums1i equals nums2j. And determine the next greater element of nums2j. Interesting. Okay, I'm definitely gonna have to learn this. Apparently Amazon asked that 18 times in the last 6 months, so. But as I mentioned, I'm sorry that you're just coming in to chill, and I do appreciate it, but I've been live for 4 hours, and I did a bunch of coding and LeetCode, so that's gonna be it for the stream. When I come back tomorrow, though, I will do, I'm gonna do next greater element, and I need to keep going on the LeetCode dynamic programming study plan. So I need to keep going on that, and then whatever else. Oh, also, I started off the stream today and yesterday with some Clash of Code. It's just kind of a fun, like, quick little contests that you can do with random people on the internet, or with a private party as well. So I'm gonna keep doing that, because that's at least like a fun way to start the stream. That's it. So yeah, Tartsky Operator, thanks for hopping in. That's gonna be the end of the stream, though, so I will be back tomorrow with more of the same. And yeah, peace.